Okay, I'd like to go through a couple things here based off some questions. Actually, the first thing I want to do here is actually go to Blackboard. Since I'm going to be posting this video up on YouTube and then just putting a link um, into the course, and I might just create a new section called YouTube videos when I create anything, um, so it's easier for you to access them. But I want to show you to make sure everyone knows how to access the Tech Live videos, because I know week one was a little bit odd here. But what we're going to do here, so you go to the course that you're looking for. So specifically, we go to the Spring EET 1100. Then we go to Tech Live and Office Hours. And then this over here is your menu. And you click on the menu, you go to recordings, and there's only one recording right now because this is for week 2. You can even see the date that it was created, so you can see it's definitely week 2. And that's where the remaining ones will be for the rest of this session. So there'll be 4 more that pop into here as we have the sessions. Now, if you look here exactly like at 3 o'clock when the session were to end, it's not going to be there precisely at 3. It's probably going to be like 3:10 or 3:15 because it takes a while for it to process all of the video information. All right, but let's get back here. I've had several questions and I tried to do my best to answer them via email, but um, they're good questions on sign conventions and knowing power. And so I want to kind of take a minute here and make sure we have here. So this is for 25 part B. So this has a resistor here. And it's got 1 volt, and then there's an arrow that's drawn here. Well, let me try and have it be a little bit more like what the book has it drawn as. So they have 10 milliamps with an arrow drawn like this. And I can see, I had a question, I can see how it's easily, there can be some confusion. Now, in the video, I said that power for resistors is always positive. And that is correct. It is always positive. But if you look at this diagram here, I think there can be some confusion here, is that it looks like the arrowhead is entering the negative terminal there. And if it's entering the negative terminal, well, wouldn't that be negative 10 times 1 volt for power? And that would get me negative 10 milliamps times 1 volt. And so I'd get negative 10 milliwatts. But no, that's not the case. In fact, the reality is this is not, let me emphasize this, arrow is not entering negative terminal. And you might say, well, it absolutely is. The first terminal it hits is the negative. But the difficulty, and this is sometimes what's a little bit, takes a little bit of getting used to, is that this arrow, the way it's drawn here, and I'll emphasize this as well, the arrow is in the resistor. I'll put quotes here, in the resistor. And so if it's already in the resistor, it's already then hit one of the terminals. Sometimes when we do these drawings, and this is the way I like to do my drawings, is instead of drawing it like the book did here, and I'll show you why this is still correct, I prefer drawing my circuit diagrams like this. To me, it makes it a little bit more clear that it's entering the positive terminal. But let's still see why this is the case. And so what I'm going to do is just create a circuit path here. And this is when you create a circuit path here, so this is a loop here. So this loop here, and actually, I mean, I could, instead of drawing it to be such like that, I'll draw it like kind of how we normally see things. So I'll draw a nice kind of box. And I know it's a short circuit at this point, so I don't care about that. There would be other circuit elements. If you want, I'll draw at least one other circuit element in here. I won't even put any kind of signs in here because, there'd have to be some kind of circuit element in that diagram. Because if you just have a resistor that you touch the two ends together, you're not going to magically get 1 volt. All right, so let's go ahead and draw the loop. And I'm going to draw the loop very large here. And so the arrow keeps going in the direction of the loop. So let me draw some of these current paths here. So these are the current paths, or this is the current path here. So what we should really see here is that we are entering the positive terminal. But what are we doing here? We're actually, here I'm going to see this, we're leaving the negative terminal. And so that particular diagram from the text can be a little confusing when you first see it. Okay. Now, there was another question, and this was just sometimes I forget that you might not think of this right away, and so I didn't necessarily bring it up. But some people can get confused on this, and it's understandable. 26 part B here. Now, first off, this is not a resistor. This is actually, so I'm just going to put here, this is not a resistor. So because it's not a resistor, the power doesn't have to be positive. The only case we know where the power has to be positive is in a resistor. This is actually an inductor. And this could be positive or negative power for an inductor. And so we have this plus minus, and this is similar to the previous problem as well. It's because the way the arrow is drawn, it makes it look like the arrow may be entering the negative terminal, but it's not entering the negative terminal, it's actually leaving the negative terminal. And so again, if you kind of draw the same little, put another circuit element in here, kind of figure like this, and we trace the current paths completely around, we can see that the arrow enters the positive terminal. So the current means we'll get that, kind of +1 in my power computation. Okay, but that's not really the issue that most people run into with this. What they run into here is that they see this little e here and they're like, what the heck is this e? Well, this e is the natural exponent and it's the inverse of the natural log. Um, at the end of the video, I'll give a little bit of information about that e because it's actually kind of there's some interesting things about that number. It's actually a very important number, not just in mathematics, but it's this is that natural exponent. Actually, the reason it's there is this absolutely describes how voltage and current often charge up or discharge across components. And it's where something that we'll talk about later in the course, talking about time constants, comes from. So natural exponents are pretty important. So let's go ahead and let's just pull up a calculator. Now your calculator is going to be different than mine. So let's just make sure here. This EXP is not the button you want to use. That EXP is for like scientific notation. So that'd be like if you had 1.6 times 10 to the, let's say, negative 20th. So that's what that EXP is. So, and apparently, even though I have it written in scientific, it's going to put all those zeros out there, which is stupid. Um, anyway, that's what this is. Now you see this here, E, that just gives you what the number E is, which is okay. I mean, you can use that on the Windows calculator, but most calculators don't have that kind of button necessarily. They might have a pi button. They don't necessarily have an E button. But you can see this ln here. And what most calculators do is they'll have like a second button that you can use. And mine's right up here. And if I hit that second button, I get e to the x. So, and typically for your calculator, it's like in like maybe yellow in the top right as far as what the function is. And so when we're figuring out the current and voltage in this, we actually have to use that function on the calculator. Now the other thing this figure has, and in the diagram, it says that t is equal to 500 milliseconds. Now this is where it can be helpful to be able to go back and forth between engineering, scientific notation, and just decimal notation. So 500 milliseconds is equal to 500 times 10 to the negative third seconds, which is what we would want to convert it to. But that's just the same thing as 0.5 seconds. And if you're not comfortable with that in your head, that's not a big deal. All you do is you're just going to type in 500 exponent 3 negative. And that's your 500 milliseconds. But if I hit equals, that gets me 0.5. All right, but let's show you how you could compute this here. So let's compute the voltage here. So on this particular calculator, let me clear everything out. I'm going to first do that exponent. So I'm going to do the 0.5, make that negative, and then I'm going to hit my second button and do e. So I'm doing e to the negative 0.5, and then it spits out a number for me. And then I'm going to multiply that by 16 negative, because that's the equation for my voltage. And I get then that my voltage is negative 9.704 volts. And then I do the same thing to compute the current, and then I can compute my power. Now, as a side note, there is something kind of interesting you can do. And if you want to, you can kind of see this and do it on your computation to see if you get the same answer. I don't ever do it this way, but you can go ahead and just say that power is equal to 8 e to the negative t times negative 16 e to the negative t. And then I'm not going to go through the algebra on how you could well, actually, I'll go ahead and do it. Well, so if we do 8 times 16, for instance, so we'd have negative 128, and then you'd have e to the minus t times e to the minus t. Well, think about it. If you have x squared times x cubed, that would be x to the fifth. You add the exponents. And so this would actually just be negative 128 e to the negative 2t. And so that's actually another way you could compute the power. But what I would probably do, because I don't want to make, for me, there's too many opportunities to make algebraic mistakes doing it the other way. And so I just use these equations here to compute the voltage and current and then multiply the answers together. And then, of course, making sure that my sign convention is correct. Now, the other question that I've had popped up, and I'm not going to go over it too much because obviously I want you to do this here. So this is question 46. And so we're given a couple graphs here. So the first one, we have a graph, and I'm not going to write the numbers down, but we have a graph that looks like this. Or it might not be the exact same thing here. But the slope here is equal to the resistance. And well, that's easy enough to do. I mean, slope is just change in the y over the change in x. So it's the change in current over the change in voltage. And just as information, that's delta is the Greek character for delta. And in mathematics, that's just referred to as change often. So when we say delta x or delta y, we're talking about what's the change in the y variable. And in this case, the y variable was current, so the change in current over the change in voltage. Making sure to keep units aligned. And actually, I'm sorry, it's not that the slope equals the resistance. I was looking at the wrong thing here. It's 1 divided by the slope equals the resistance. So so the slope is equal to the change in y over the change in x, which is the change in current over the change in voltage. So the resistance change in voltage over the change in current. Now, parts B and C for this here give you some diagrams that are trying to, quote, trick you in some sense, but in other senses, they're not necessarily trying to trick you, they're just trying to see if you can figure out what's going on here. And so this is 0 volts. And so if we look at the resistance here, if we have the change in voltage over the change in current here, well, I would just have the change in voltage, but the current doesn't change. The current is actually always 0 amps. Now, this is mathematically impossible. But we're in the real world, not in the theoretical world. So what that would mean here is that this would actually have, well, a very large resistance. And what's the largest resistance that you could possibly have? What's the, quote, the biggest number? It's not really a number, but think of it as the biggest number possible. And this, I will give you a hint, this leads to a condition called an open circuit. And just kind of think like there is no biggest number out there. So what do we use to represent the biggest number? Now in this case, the change in the voltage is 0, and I'm going to have change in current. But you can do that computation. It doesn't matter what the denominator is there. Do some examples. Do 0 divided by 4, 0 divided by 5, see what you get. And you'll get a resistance. And in this case, this is indicating a short circuit. So I hope that helps with some of the homework problems. And keep up the good work and keep asking questions if you have them.